So once again, so thank you very much, Olga and the organizers for the invitation. So this is not my usual community, so I will try to expose why you can actually combine Internet of Things actually with high-performance computing and make everything work together. I was also quite shocked that we typically tend to have young participants, but I was not sure that we will have 11 years old in our conference. So having said that, I will try to actually illustrate everything up to 11 years old. So anybody should, after 11, hopefully can understand what I'm trying to explain here. So the idea of the talk is going to be how to design data centers today. So if we try to design data centers, it's actually a very challenging task because very often you don't know what is going to come, actually the resources you're going to use, and also what type of failures are going to come in the data center. So if you look at the structure today, what you have in current ICT or IT ecosystem, where you have a number of sensors that are actually coming, or a number of devices that are coming, like tablets, phones, and so on, that try to operate. And very often, they don't really operate alone. So what they do, they communicate what is called actually the edge. They communicate with switching centers or intermediate level centers, and then in the end, they finalize the whole process going. If it works to work this guy, here it is. I'm not sure you can see it from the back. They finish in these hyperscale data centers. So the whole talk is going to be about how to design these hyperscale data centers that big players like Amazon, Google, and so on have to design. The key point here is that you want to, of course, optimize the energy, and you also want to minimize carbon footprint while making sure that the system is reliable. You have to actually make sure that you can keep operation 100% of the time. So if we think about it, you say, okay, well, if there was this energy problem now, I'm not talking about Russia, that's another story, but if we think about in general, there was an energy problem already for like few years. Why? We have been building computers for more than 40, 50 years. So, and the reason is, in the past, the IT industry was relying on a very particular law that was actually created or discussed by Gordon Moore. I would not really advocate it's a law like in physics, but the idea is that you can put more transistors on a chip, and that's why we have the iPhone and these type of things. And you can actually have these transistors reduce in size, but you don't increase the power, because the power was reduced by half for every transistor. Okay? This is what is called Moore's law. So that was happening every 2 years. More or less, you could have a new generation of processors where you reduce the size, and you also reduce the amount of power it consumes. Now, that was working very well until around 2011. So there was actually projections of how much you would reduce power. And every 5 years, it was actually created by the ATRS for the semiconductor industry. And in 2011, 2012, they started seeing a quite significant mismatch, which is the point that you see here. So this mismatch, what we're basically saying is that we are not able to reduce the power consumption anymore for these transistors. You reduce them in size, but still they consume pretty much the same thing, or almost the same thing. And in fact, at that moment, the overall, if you build a computer in 2011, from the original projections, you will be consuming 40% more power than was supposed to be. The reason, there are multiple reasons. I'm not going to enter into the technical details, but it's basically leakage. So even if you are not doing anything, you do the thing so small that it leaks power all over the place, even if you're not doing anything. Now, if you think about that, the consequences are today, this difference between what was projected, which is what you see flat, and what is actually, the reality today, you have more than 80% variation. So the power density, you made the transistors smaller, you made them fit in a smaller size, but the power consumption is significantly higher. So what is the result? The result is that you have today a big problem of power density and temperature. This is a new challenge that came up in the last 10 years for data centers. Now, we have to combine this with the problem that, well, cloud is everywhere, and the big players keep growing. So you think about Amazon, they just reported 2021, $1 billion profit last year, and they're expecting to grow even more this year. So, and then as a result, you say, well, this is only in the US. It's not true. You think about, this is the projections for the European Commission. So what shows is that you are having this year, the last 2 years, growing almost 30% on the amount of personal computers, but infrastructure as a service, which is data centers, these big data centers, they are growing at a factor which is much larger. So basically, data centers are deployed everywhere. Now we have to actually find a way on this new trend, because people are not going to reduce the amount of computing they do, how to reduce this and make the systems reliable. And that's the idea. So when you think of it, okay, so how do they work? Very simple. Data centers are large. This is actually the equivalent, one of the latest data centers of Microsoft. It doesn't show the scale, but this is equivalent to 7 football stadiums. Okay, all together. This is actually a data center. And you see the energy comes all over the place, and also you have all these corners here on the sides, if it doesn't work, this one, all this part, which is where you bring in and out new servers. So actually the servers keep coming in, and you keep filling it completely. Now, how do they work? Full speed all the time, to make sure that you can supply all the requests that actually are coming in. Now, this with current trends means that, as I told you, power consumption is going down. It's actually growing really dramatically up to a point that it's projected there's going to be around 7-8% by 2030. I say, well, that's life. So it's going to grow in amount of power because you have to do more computing. But the truth is that it's really surprising. But if you take big players, Google, Alibaba, you look at how much they really use these servers, the utilization of these servers is around 60%, 60, 65, no more than that. So basically, at least you're losing 1/3 of the power that the servers are full throttle, but they're not fully loaded. They're not doing computing. You say, why are you not doing computing? Well, that's the problem. You have 60, 65% capacity because you have a lot of inefficiencies in the design of data centers. And also you want to make sure the data center doesn't collapse. And because you are uncertain of these heat and power densities, you tend to really overcool the system, and you're not really using the servers at the full speed. That's the current trend. So the idea is that how do you design a data center? So here you see the structure. You have the level at the bottom where you have the resources. Then you start having the operating system, the virtual machine management. You have some kind of higher level hypervisor that controls how these servers are allocated for clients. The more you pay, of course, the more priority you get. And then you have all these layers on top, cloud services and so on, scientific, but also YouTube and so on. And then you start trying to think, okay, how do you optimize this? Well, the first typical way has been done for 30 years is every layer works on its own. Why? Because it's complicated to propagate dependencies, so let's give margins, design margins, and then you actually leave everybody work on its own alone. So obviously this is not suboptimal. This is not optimal, it's very suboptimal. You have a problem which is a multi-scale modeling, which is actually an area that in this community comes very clear. So you have to understand the component choices, the applications, how they interact, what are the dependencies that they have to actually make the system work efficiently. But there's no clear communication of knowledge between the layers. Now, if you think about IT equipment, they are also interestingly designed completely separated or over-provisioned with respect to actually what they need, but the cooling as well. So they will put, you cannot really have your, because it's not allowed today, you cannot have your home or normal public spaces working at a very low temperature with cooling, because it's obviously we are trying to reduce power. These guys operate at 16, 17 degrees. So it's a huge vacuum bag and actually all the cooling, which is at 16, 17 degrees. You enter there, you have to put a jacket. There's no way to actually enter in these guys. Why? Because you want to make it cool, to make sure it doesn't fail. Now, as a result of that, you only don't have the problem of inefficiency on the part that you're not using it full speed, but the fact that you also have an overexpenditure in cooling and thermal management, to the point that almost 35% of the energy is actually spent on these inefficiencies. You take one of the big guys, for example, an 18 megawatt data centers, like the one I show you, you can definitely waste, at least it's estimated, $2.53 million just simply wasted on cooling. It's significant. If you think about that there are these, just in the case, for example, of Microsoft, they spent in the last year enough money to actually build 17 data centers. If you think about the money that goes there in efficiencies, it's dramatic. Now, how can we improve that? Well, there are multiple ways. The typical way that some people are becoming very innovative is, well, we want to make sure that the system is not very hot. Let's put it underwater. There is actually a new design that actually Microsoft has proposed. They are actually really sinking their data centers. It's okay, but you have a bit of problems of management. So actually having scuba divers controlling your servers and so on is not the most ideal way, but it's an idea. I would propose something else. Why don't we try to do something with all the connectivity that we have today, these sensors, and try to do a global management? And that's the idea of the talk today. So this is this was a new project sponsored by the European Commission and the Swiss Confederation 5 years back. What the idea was to come up with a design of thermal-aware data centers, considering how you can actually improve monitoring and at the same time the interrelationship between the different levels. So this includes 3 phases. We have to first create enough monitoring infrastructure to be able to see what's going on in the data center, to detect the power consumption when there are elements that are not working properly and they can fail. We have to then create models for this type of behaviors to understand what's going on. And finally, you have to optimize. And how do we optimize? We optimize 2 parts. First, at the level of the server, so the computers, put it this way. We have to understand how they degrade and the possible failure rates that they have so that we can predict when it's going to fail. Instead of overcooling it and actually making sure it doesn't fail, we operate normally and we predict when it's going to fail and we try to replace it before it happens. And the second part is that once we have done that, can we then optimize further? And we use multi-agent reinforcement learning for this to make sure that once we know the type of workloads that come in, try to even increase the amount of power that goes used on the power without saturating the whole system. That's the idea, to increase utilization. So this is the idea. So you first have a number of applications that arrive. You have a monitoring infrastructure that I will explain in a second, which is a power monitoring system and management, PMSM. Then you actually use this information to create power and thermal modeling tools that you can actually use to derive your models. And finally, with this information, you apply multiple agents that actually are able to control frequency, power management, voltage in the different parts, as well as the cooling infrastructure, and then you try to optimize at runtime what's going on. So the idea is like I said, so we have to first start seeing what is there. So generally, servers, they have some sensors, but they are not too many, and typically they are on board. They are typically for just core parts like the processor, the memory, but you don't see the relationship for the other parts that are actually on the system. So we created our own infrastructure to monitor 3 data centers. In this case, we have a particular customer that was very sensitive about wasting money, which is banks. So we have Credit Suisse, that when we told them and we showed them the graphs that they could actually save $3 million for every data center they have in Switzerland, they have 3, they said, okay, let's go for it. So we actually created the infrastructure. We developed an infrastructure to monitor whatever was there, but we added additional Internet of Things sensors connected for monitoring temperature, humidity, and vibrations at the level of the racks, which is not the level of the server, but really the racks, how they operate. And then we actually had to power up. So you cannot really replace in batteries, so we created systems that you clap on the wires that are running around in the whole data center, and have a supercapacitor, which is what you see here, and will be loaded, and as soon as it loads, it will connect to the network, and it will start talking to the other sensors. And then we have all these sensors connected, and we will actually be able to create a system-level monitoring infrastructure that you can see, you can collect, and you can show to the manager of the data center, and for us to create these frameworks, what was going on. And you have actually, I put you a link where you can see a few videos of the system running and so on that we just finished actually last year. So then what you have is something like this. So you were able to create graphs with the energy that is going on in each of the rooms in the data center. And then what we had in the first place was what you saw here. So we have all these are warnings telling you that something can be done better. So basically, we have alerts in every single room saying this management is not done properly. So you have to do something with it. So what you will have is graphs, like the one that you have here, which seems pretty reasonable in the sense that the data center energy is, if I can manage, I think it's better with the thing here. What you have is this type of graphs that you have, which is very flat, so which is actually good. You want to always consume the same amount of power, but in reality, what you see is that the energy that goes, this is really oscillating. So the servers are really powering up, powering down, powering up, powering down, which is a lot of problems from the point of view of thermal behavior and reliability. And the reason is that the assignment of works to the servers and so on was not done properly. They were not able to have a good characterization of the behavior, and as a result, there's a huge oscillation. But they were not seeing this because they were not having these sensors. In this case, we have roughly 20 sensors per rack, additionally to what was there, and we'll correlate all the sensors to create these graphs. Let me give you another example, so even more dramatic, which is what we could see failure of servers, and we could also see what is called zombie servers. Zombie servers, which is an interesting terminology that is used in these hyperscalers, are servers that you have so many servers there, and these servers are there doing nothing. They're basically consuming most of the power, but they're basically not doing much. Why? because the energy that goes in a server, if you're not in utilization close to 80%, you still pretty much consume almost the same thing, but you're not doing any processing that is really useful or justifies the effort that actually is spending the energy on you. Okay? So what you see here is that you have some heavily utilized servers, but so many others. This is the amount of computing that you come out for power that you use. You have some highly utilized servers in some of the racks. You see the ones that you have. These are 3 racks, but some others that are really underutilized. They are below 40%. So they consume almost 95% of the energy of a really utilized server, but they actually are doing only 30 to 40% of work. And the reason for that, like I said, is why do we have only like 20% of heavily utilized servers in a range of a data center of more than 7,000? And the problem is system reliability challenges. How do you model when these systems fail? You want to make sure they don't fail, so whenever there is a chance that they will collapse, they have to operate at least without a stop for 3 years. So imagine your laptop without switching it off for 3 years, and they don't have good models for that. So we started by creating the models. So you think about mean time to failures. What are the factors? The traditional models that were created, that were understood in semiconductor electronics is typical behaviors of stress of the materials. So time-dependent electric breakdown, this type of factors that is really at the chip level. But then when you think about the server, because of the thermal stress and the high power density, there are many other factors. Which factors are those? The first one is what is called, the overall concept is called thermal stress. Thermal stress has 3 factors. Spatial and thermal gradients, which are basically one part of the chip is very hot, the other part of the chip is very cold, and then automatically there's a difference of temperature that affects the resilience of the whole chip, and it will collapse. And by the way, what will happen is that your fan, that's why sometimes even on the laptop you hit, starts, why? Because it's trying to cool down one little part of the chip, but it's cooling down the whole server or the whole processor, even though it's not needed. Now, the second one is what is called temporal thermal gradients. And this is what happens when you want to optimize power. You typically save power by how? Switching off components in servers. So you have a part where the system starts heating up. Then you say, oh, I want to switch off the power. I want to save power because I don't think it's really needed this server. Then automatically the temperature goes down. So these different changes of temperature is what is called thermal cycling. And it's actually also affecting a lot the resilience of the chip. It's like you put something in the microwave because the servers heat up to 120, 130 degrees, and you put it down to 45, 50. And you do it repeatedly. Every 2 seconds, 3 seconds goes on like this. Okay? So this actually creates another problem. Of course, the thermal cycling, it depends on how much is the amplitude and frequency. In latest servers, you can have oscillations of more than 40 degrees. So imagine materials actually exposed to 40 degrees temperature changes in the order of a couple of seconds. So that's also affecting a lot. So overall, what turns out is that the usual models for mean time to failure of devices of semi-electronics, which are typically using the normal models for, and that they want to do electromigration, TDDV, and so on, they are not at all related to what really happens on servers. The servers are mostly affected by this new trend, which is the thermal stress. And that's why you calculate in detail the mean time to failure of these servers, and they really follow the trend of the thermal stress components. So that's what we created. We created new models for this type of threats that happen in the system, and we created the first manager that was called the SPOT, which is thermal stress aware power and thermal management, which is not anymore only focusing about reducing power, but is reducing power and keeping into account all these additional factors. And then what we do is we consolidate, we have first an analysis of the workloads, then we look at how much is the thermal stress that we have on the different parts of the chip. We try to make sure that we control the peak temperature, but we don't oscillate so much the heat. And in the end, we actually apply frequency and voltage scaling, so DBFS, whenever it's possible. But only whenever it's possible if it's not going to affect reliability. So overall, what you get with these things is interesting. So this was a result that we published with Intel. They were quite surprised even themselves, because they do very detailed characterization at the chip level or at the transistor level. But when you go at the global server level, they were not exposed to that. So you see they will actually try to minimize power by what? By having a couple of processors running full speed, the other ones are off. So what will happen is that you will have a huge problem because these 2 guys that are running full speed most of the time will be the ones that will be making the system fail and create these zombie, actually, servers. So what we did is like we created a system that will spread a little bit more the workload, so a little bit better managed in the sense, well, managed. You use a little bit more power because you are not really being so efficient maybe on power, but you dramatically improve the resilience and the robustness of the mean time to failure, to the point that you can improve by 49%, almost 50% the reliability of these servers. There is a trend there that you say you replace, rule of thumb in a data center, every 3 years you have to replace servers, which I'm not going to enter into wastage and what is going to be affecting the planet. But the reality is that you can do much better than that. And the new data centers, we can actually guarantee that you have servers operating for 6-7 years without any problem, thanks to this. Now, then the next one is, okay, so we have done that, but still we are not using full throttle. You remember we have 1/3 of the computing power that is not used, and this really depends on the application. There was never a link between the applications and the actual way that the server works. So we created a multi-end reinforcement learning model, which is called Mammoth. Why? Because Mammoth is the one that typically in the tradition, what is called, there's one leader and everybody follows. So that we try to actually create a rule that everybody will follow how to do this thing more efficiently. The idea is that we have the application knowledge, how much is the quality of service, and what is the requirements of the amount of energy that you can spend. We will have the control of the frequency of the processor, and we can have also parameters from the application. We can change how fast the application runs, how slow, and so on. So we can have tuning knobs at the server levels, but also at the application level. So all this link that was not existing between application and servers. And we created a few agents that will actually work. So we'll have to first learn how the application works, and we will, at runtime, we'll be changing all these parameters all together. If those are going to have the details, I will let you know, but I mean, I can give you more details, but since I don't have more time, just to show you briefly the results before Olga has to kick me out of this. So here are the results. So what you see is the state of the art. Typically, you will try to do power management, and overall, you will have a server utilization that, as you see, is pretty low. Typically, like I showed you before, if you are very good on that, you will have maximum, or typically many servers with different types of servers, 40, 50%, maybe 60. Well, with Mammoth, we managed to reach almost 97% utilization. And without destroying the server, because destroying the server is guaranteed by the spot that is actually running on parallel. And then when you think about how much you can use effectively the power, and this is what you see here on the side, what you have is overall actually using less power, because for these racks, this is the state of the art. This is how much we need for our multi-agent system, Mammoth. Why? Because we are not cooling so much. We actually are making the system use the effective cooling they need and the temperature that is there. And actually we propose, has not been approved, but we propose for the ARRAI, which is the standardization of data centers, to operate the data centers at 25 degrees. Because it's unfair that you cannot go in a bar with a cooling, and actually data centers are cooled down. So why don't we actually put the constraints on everybody the same way? And that was actually the target. They are discussing about it. Hopefully they will agree. But the idea is that in the end, what I would like to show you, I hope I have convinced you, is that we can definitely create green and energy efficient data centers, and it's a dramatic request that we have today for the problems that we have, but we have to understand how cooling and servers operate. There is clearly a suboptimal design that has to be done by using modeling and integration on multiple levels. And clearly also for resilience, what this was the claim benefit of doing this type of separation is not the case. So you have to really take into account everything together, try to model everything at the same time, and try to see how to apply cross-layer optimizations like I show you. And as I presented you, this requires IoT. You need to have new sensors. So now we have convinced HPE to buy the whole design that we had done for racks. So actually data centers will have many more sensors than what they actually were in the past. And not only about sensors, but it's the rack and the whole room that needs to be monitored. We need to find models for that. That's a little bit like what we did. You have to take into account thermal stress at the same time as power management. It's not as simple as I reduce power and it works. You have to minimize also the thermal stress to make sure that the system can be maintained properly. And finally, you have to optimize the whole data center together, which is what we did with Mammoth. And here, just as a proof that sometimes we manage to succeed even with the big players. So this is actually a project that finished 2 years back, and showing the results and having the banks behind us, we managed to convince Eaton, which is one of the biggest providers worldwide, to start including our monitoring infrastructure on their own products. So I hope that this is a good example. I'm talking now to Google, so let's see what they can do with that. So thank you very much. If you have any questions, I'm happy to actually talk about it.
Thank you.